You look at a skyscraper and assume the limit is strength. At some point, the building just gets too heavy and crushes itself, right? That's the obvious answer, and it is wrong. The Burj Khalifa stands at 828 meters, and the engineer who designed it has said a structure could reach 3,000 meters, almost 2 miles. So the technology is not the problem. The materials are not the problem. Then what is? Here's what nobody tells you. The real barriers to a mile-high building aren't about steel and concrete. They're about wind behaving like a musical instrument, elevators that can't support the weight of their own rope, concrete that has to be pumped at night and packed with ice just to keep it from hardening too fast, and a price tag so massive it reads like a typo. Every limit is solvable, but each one is stranger than the last. Here's the thing most people get wrong about tall buildings. They assume the enemy is weight. They think that at some point the structure just can't hold itself up anymore. But the actual governing force on every super tall building isn't gravity. It's AIR. Wind is what controls how high you can go, and engineers don't just fight it, they trick it. The entire exterior of a super tall is shaped to confuse wind, to break up the swirling vortices that form when air hits a flat surface at speed. Some buildings use textured facades, others cut holes in themselves. At 432 Park Avenue in New York, there are entire floors with nothing on them. No walls, no furniture, no people. They're called jump floors, and their only job is to let wind pass straight through the building to reduce the lateral forces trying to push it sideways. Empty floors in a city where rent is measured by the square inch. That's how serious wind is. But here's where the story gets wild. When the Burj Khalifa was being designed, the original spiral went clockwise. It looked right. The math checked out on paper. Then they put a model in a wind tunnel, and the results came back ugly. The forces were too large. The motion was too large. So they flipped the entire spiral to counterclockwise. That single change didn't just fix the problem. It let them add 300 meters of height to the building. That's the entire height of the Eiffel Tower, unlocked by reversing a spiral. And here's the part that nobody talks about. If the first design had worked fine, they probably would have stopped there. The building exists at its current height because the original plan failed. Failure literally made it taller. But shaping the outside only gets you so far. Some buildings need a hidden weapon buried deep inside. At the top of some of the tallest buildings in the world, hidden behind locked doors that only engineers and technicians ever open, there are massive objects just sitting there. Not mechanical rooms, not antenna equipment, giant, precisely weighted monoliths designed to move. They're called tuned mass dampers, and they work like a pendulum swinging in the opposite direction of whatever the wind is doing to the building. Every single one is custom built because every building vibrates differently. Think of it like a crystal wine glass. Flick it with your finger and it rings at a specific pitch. That pitch is the glass's natural frequency. Every skyscraper has one too, and if the wind hits it at just the right rhythm, the building starts to resonate. That's when people on the upper floors feel the sway. Not dangerous, but deeply unsettling when you're trying to sleep on the 80th floor. The solutions are fascinating and completely different from each other. Taipei 101 has a giant golden sphere suspended between floors that visitors can actually go see. Shanghai Tower uses electromagnets to adjust its damper in real time. One Vanderbilt in New York has a 500-ton block of steel engineered to handle a direct hurricane hit at 110 miles per hour. That's 1 million pounds of metal sitting quietly at the top of Manhattan. But here's the twist. The Burj Khalifa doesn't have one. Its three-legged buttress core design combined with its wind-confusing shape makes a damper unnecessary. The building handles it on its own. A mile-high tower almost certainly won't have that luxury. It would likely need multiple dampers stacked at different heights. And here's the part worth remembering. None of this is about preventing collapse. It's about comfort. It's about making sure someone living on the 200th floor doesn't feel seasick in their own apartment. That comfort costs a fortune. Now you've shaped the building against the wind and hung a 1,000,000-pound pendulum at the top. The outside is handled. The inside is dampened. But what is this thing actually standing on? Here's the problem nobody sees. Tall buildings are built in cities. Cities are built in river valleys near ports. And river valleys have some of the worst soil on the planet. So the tallest structures in the world are often sitting on the worst possible ground. The Petronas Towers in Malaysia had to physically move their entire building site 60 meters just to find the right kind of rock underneath. Then they drove 104 concrete piles as deep as 114 meters into the earth. That means 25% of the building's total height is buried underground where no one will ever see it. That's the foundation game. It's not about digging deeper. It's about finding ground that won't betray you. Then there's the concrete itself. Modern ultra-high performance concrete is 10 to 30 times stronger than what existed in the 1950s, thanks partly to additives called superplasticizers that reduce the water content and make it dramatically harder. In theory, it can support a mile-high structure if it's thick enough, but strength means nothing if you can't get it up there. During the Burj Khalifa's construction, concrete had to be pumped to extreme heights using specialized high-pressure systems. The desert heat made it cure too fast, so crews filled it with ice chips and only pumped at night. That's not a metaphor. They literally iced the concrete like a cooler full of drinks. At the Jeddah Tower, currently under construction, the challenge is even worse. Getting concrete above a kilometer is a core design problem, and there's no fixing mistakes after the pour. One error at that scale multiplies 1,000 times. The margin for failure is essentially zero. So the wind is managed, the damper is tuned, the concrete reaches the top. You would think the hard part is over. It is not even close. The real bottleneck for a mile-high building is not structural at all. It is how people get to their floor. In a 500-meter elevator shaft, the steel rope alone weighs around 27,000 kilograms. That is roughly 60,000 pounds of cable just hanging there before a single passenger steps inside. And beyond 500 meters, the elevator physically cannot support the weight of its own rope. That is the ceiling, not the building ceiling. The elevators, it just stops working. The workaround right now is sky lobbies. You ride one elevator partway up, step out, cross a lobby, and get into a different elevator that takes you higher. It functions, but every sky lobby eats valuable floor space in a building where every square meter costs a fortune. And nobody paying premium rent on the 180th floor wants to transfer elevators twice just to get home. That is not luxury living. That is a commute inside your own building. A carbon fiber rope called Ultra Rope pushes the limit to about 1 kilometer and is planned for the Jeddah Tower. But a mile is 1,609 meters, still out of reach. Frank Lloyd Wright actually tackled this problem back in the 1950s when he designed a mile-high tower called the Illinois. His solution was 76 atomic-powered elevators, each 5 stories tall, mounted on rails like vertical trains moving at 1 mile per minute. Visionary and completely impractical for his time, but the rail concept is now being explored seriously. Here's the real issue. Until vertical transportation is fully solved, every floor above 500 meters is a logistics problem stacked on top of an engineering problem. The building can stand, the people just can't get up it, and there's still one more barrier nobody talks about. Here's a question that should make you uncomfortable. How long does a skyscraper actually last? Most people assume forever. The answer is about 100 years by design. But the average 200-meter building gets seriously considered for demolition at just 41 years old. That's not a typo. A structure that took years to build and cost hundreds of millions of dollars starts looking like a teardown before it's middle-aged. And the taller the building, the more expensive every single year of its life becomes. Retrofitting is where the numbers get brutal. The Empire State Building's modernization over the last few decades cost over $1 billion, and that building is only 443 meters tall. Now scale that to a mile. The maintenance costs alone would be staggering, and they never stop. They just grow. But here's the part that really sharpens the problem. The Jeddah Tower has been under construction for over 14 years. During that time, the elevator technology spec'd at the start has changed. The mechanical systems have changed. The plumbing engineering has evolved. Every expert involved in the project has watched their original plans become outdated while the building was still going up. A mile-high skyscraper might take 20 years or more to complete. By the time the top floors are finished, the lower floors are already running on yesterday's technology. You're essentially building a structure that starts aging before it's done. And then there's the question nobody in the industry wants to answer out loud. What happens to the Burj Khalifa in 100 years when it gets too costly to maintain? Does someone spend billions tearing it down, or does the tallest building in the world just slowly crumble? The taller you build, the harder that question hits. Every record-breaking tower is also a record-breaking maintenance commitment with no exit strategy. But even this bows to one final limit: string. And that's the real tension. Developers can make safe, reliable money building normal height buildings. Going super tall is always a gamble, and the payoff isn't just financial, it's symbolic. You can't picture Paris without the Eiffel Tower. You can't think of Dubai without the Burj. These buildings are flags planted in the ground. They tell the world we're here. Every engineer interviewed for this topic said the same thing. A mile-high tower isn't a question of if, it's a question of when. And when means when someone decides the statement is worth the check. So here's where you land. You started thinking the limit was physical: steel, concrete, gravity. But what's actually standing between us and a mile-high building is far stranger. Wind that plays a building like an instrument. Elevators that collapse under the weight of their own rope. Concrete that has to be iced and pumped in the dark. Structures that start aging before the top floor is even finished. And a price tag that makes entire governments pause. Every single one of those problems has a solution. Engineers have said so repeatedly. The tallest building in the world right now is 828 meters. The man who designed it says 3,000 is possible. That gap between what we can build and what we choose to build is where every future record lives. And it always comes down to the same question: who's willing to write the check? If you found this interesting, subscribe for more.